kiddos, welcome back, and we're about to start a new chapter. We're going to start our chapter on thermodynamics, one of my more favorite chapters of the year. We're going to start by talking about the heat of a reaction, or the enthalpy of a reaction. Enthalpy is synonymous with the word heat. So let me give you a generic equation. Let's say I have reactants A and B, and they react to form my products C and D. Along with that, heat could either be produced or it could be consumed. We symbolize that with this symbol, delta H. You've seen it earlier in the year when we talked about evaporation and condensation. Maybe you remember that. To calculate delta H, we take whatever the heat content is in the bonds of our products, and we would subtract that from the heat content of our reactants. Whatever's left over is the delta H of my reaction. Now, as you can imagine, that could be a positive number, or it might be a negative number. So let's talk about those two scenarios. So let's talk about this one here, where the heat content of my products is greater than the heat content of my reactants. Alrighty, so let's take a look at this graph right here on the right. My products have a higher enthalpy, or heat content, than my reactants. Where did that energy come from for my reactants to turn into products? My products have more energy than my reactants. That energy had to come from somewhere. That's right. It is consumed or added from the surroundings. Because of that, we say that delta H has a positive sign, and the reaction is called endothermic. Okay, it's added from the surroundings, and those reactions are called endothermic reactions. Their sign would be positive. Hopefully you can see why. My reactants have a low enthalpy. My products have a higher enthalpy, so we have to add energy from somewhere, and that comes from the surroundings. Now, what about the opposite? What if my reactants have a higher heat content than my products? So that would be this first graph over here. Here are my reactants with a particular enthalpy, and my products have a lower enthalpy. What happens to all that extra energy? Where does it go? That's right, heat is released to the surroundings. Delta H has a negative sign, and those reactions are called exothermic. So we have exothermic, where energy is released, and we have endothermic, where energy is added. Now, let me give you a couple of examples you might be familiar with. Heat packs and cold packs. Heat pack reactions take elemental iron and elemental oxygen. When they're mixed together, they react to form iron 3 oxide. Now take a look at the graph I've drawn here for you. My reactants have a higher enthalpy than my products. My reactants start out up here, and the products end up with an enthalpy way down there. What happens to that energy? Yeah, that's right, it's released to the surroundings. So the sign is negative, and we call those exothermic reactions. So in exothermic reactions, you will see that delta H will always have a negative sign. Its value will be smaller than 0. Okay, how about cold packs? Well, in my cold packs, notice my reactants start with an enthalpy that's low, and they end up with a higher enthalpy. My products have a greater heat content than my reactants. Well, where does that energy come from? That's right, heat has to come from the surroundings. So the sign there is positive because we're adding heat from the surroundings. We call those endothermic processes, and the sign for delta H will always be bigger than 0, or positive for endothermic reactions or processes. Now, I'm going to show you guys a video I made several years ago. I light a propane torch, And as you can imagine, when propane is lit, that's a combustion reaction, it gives off lots of energy. So I start with an exothermic reaction. Heat is being released to the surroundings. But if you notice the brass tip of my propane torch, there's a liquid dripping out of it. And that liquid is evaporating on that tip at the same time as the combustion reaction is occurring. Now you might remember that evaporation is a cooling process. Heat comes from the surroundings, and so that brass tip gets cold. And so you will also see an endothermic process in this demonstration. I think you'll find it fun to watch. So let's watch that video, and then we'll come back and we'll talk more about thermodynamics. See you in a second. Okay, propane torch, we'll turn it on just a little bit. Add a little activation energy, get the reaction started, turn it down, watch out for my projector there. And you can see that lots of heat and light are being released. Of course, if I open up the valve, we'll have more propane reacting with the air. And can you guys feel the radiant heat? Now the fun part. I'm going to open this up even more. And now this becomes somewhat interesting. Keep in mind, the propane in this container is pressurized, so it's actually liquefied in this container. Watch. Now look right here. You see right there? Yeah. You see the liquid drop? Now I need someone that really trusts me. Who really trusts me? In the front row.
Mandy.
Mandy, hold on your arm for me. Roll up your sleeve and hold on your arm. Trust me, don't you? Because this is white hot. Does that hurt?
No.
What does it feel like?
Cold.
In fact, look at the tip.
It's freezing.
What does the tip look like? Hold out your arm. It doesn't hurt, does
I
it?
thought he was going to pour it on my hand and light my hand.
Yeah.
Question is, why is that so cold? Shouldn't be cold. I mean, it got so cold. Right now, you guys have warmed it up with your arms, but it got so cold, there was water vapor that not only condensed on the brass fitting, but actually froze to the brass fitting. We saw crystals of water there. Relates to an earlier demonstration, the non-burning rag. What was happening here? What was that liquid doing? Did it stay a liquid? What did that liquid turn into? A vapor. When a liquid turns into a vapor, we call that evaporation. Evaporation does what? Does it require heat or does it give off heat? It requires heat. It's a cooling process. What does it cool? It cools the surroundings. Was the brass fitting part of my surroundings? Yeah. Cooled it so much, and it has a very high vapor pressure. It evaporated very quickly. That means the brass fitting cooled very quickly. And instead of being hot, as your mind told you it would be, it was actually quite cold, wasn't it? Okay. So just a quick demo showing you combustion and evaporation. Okay. Did you like that? Yeah, that was sort of fun. All right. Well, let's move on and let's talk about something called heat or enthalpy of formation. That's symbolized with this delta H sub F. The definition of heat of formation is actually pretty important, so make sure, kiddos, that you remember this. The definition of heat of formation is the enthalpy, now remember, enthalpy means heat, required or released when 1 mole of a compound is formed from its elements. So it's the heat required, we got the D there, or released when 1 mole of a compound is formed or created from its elements. That's called heat of formation. Let me give you an example, and there's a small typo in your notes you're going to have to fix. The heat of formation of the compound nitrogen oxide is 91.3 kilojoules per mole. That means that 91.3 kilojoules of energy is absorbed. How do I know it's absorbed? Well, because the delta H for that process was positive. So I know it was added or absorbed from the surroundings. So 91.3 kilojoules of energy is absorbed when 1 mole of nitrogen oxide is made from its elements. Here's the reaction, and it's going to look a little different to you today because we're using fractions to balance the equation, and that's because of my definition for heat of formation. I am making 1 mole of NO from its elements. Now, to make 1 mole of NO, remember, elemental nitrogen is diatomic and so is elemental oxygen. They're N2 and O2. So to make 1 mole of my compound from its elements, I only need a half of a mole of N2 and a half a mole of O2. Now when those react together to form my compound NO, 91.3 kilojoules of energy is required for that to happen. That is an endothermic process. Now, what would happen if I wanted to make 2 moles of NO? Yeah, so let's write the equation. I want to make 2 moles of NO. Wouldn't I need a full mole of nitrogen and a full mole of oxygen? Do you think the energy required would be more, less, or equal to 91.3? Yeah, if you said more, you are correct because I'm making twice as much. So the delta H for this process would be 2 times 91.3 kilojoules, which is 182.6 kilojoules, positive still, for that reaction. I'm just making twice as much. Okay, let's do another one. Let's do methane. So the heat of formation of CH4, CH4 carbon tetrahydride, the common name is methane. Now that heat of formation is a negative 74.8. Now once again, there's a typo here. This should actually be negative 74.6. Sorry. This means that 74.6 kilojoules of energy is released. How do I know it's released? Well, because the sign for delta H is negative when 1 mole of methane is made from its elements. So let's write the reaction for that. 1 mole of methane from its elements. Well, what elements make up CH4? Well, obviously carbon and hydrogen. Carbon's not diatomic, so that's just C. Hydrogen is, so that's H2. To balance this, to produce 1 mole of my product, I need to put a 2 in front of H2. Now, when that happens, this much energy would be released. 74.6 kilojoules would be released to the surroundings. It's exothermic. Now, take a look at this next question. How much energy would be consumed if 2 moles of CH4 were decomposed? Remember, decomposition is the opposite of formation. So I'm going to start with CH4 on this side, in fact, 2 moles of them, and I'm going to decompose it into its elements, carbon and hydrogen. See, I've written that reaction up top backwards, and I'm decomposing 2 moles of methane. So to balance that, I need to put a 2 in front of carbon and a 2 in front of H2. What would the delta H of this reaction be? Well, I am decomposing twice as much CH4, so you are correct. It would be, the magnitude would be 2 times that number. However, the sign would be positive. Why would the sign be positive? Yeah, the law of conservation of energy. If we give off 74.6 kilojoules of energy when I produce methane, when I decompose methane into its elements, that means I must go ahead and consume 74.6 kilojoules of energy. So the sign changes. So 74.6 times 2, the heat of decomposition of 2 moles of CH4 would be positive 149.2 kilojoules. Am I making some sense here? All right. Well, let's see if you can do one of these on your own. Let's try example 3. The heat of formation of methanol, CH3OH, is negative 238.7 kilojoules per mole. Why don't you pause the video and see if you can write the reaction showing the formation of 1 mole of this compound from its elements. All right, go ahead and try it. See you in a sec. All right, welcome back. Let's see, let's draw an arrow here, and let's see, I want to form it. So I'm going to put my CH3OH on the product side. What am I going to form it from? Well, it's elements. So what are the elements that make methanol? CH3OH. Yeah, carbon's one of the elements. Good job. Another element, H, well, you better write H2, right? Because it's diatomic. And the other element is oxygen, so that's O2. All right, well, let's balance this to make 1 mole of my compound. So I need 1 carbon, which is what I have, a total of 4 hydrogens, so let's put a 2 in front of H2. And I only need 1 oxygen, so how about a half in front of the O2? Yeah, that would be the heat of formation reaction of methanol. Now the delta H for this reaction would be negative 238.7 kilojoules because we are forming 1 mole of methanol, and the heat of formation of 1 mole of methanol is negative 238.7. Now, on the table at the bottom of this page, you are going to see lots of heats of formation values. I have the heat of formation of several different compounds. You will notice, though, when you come across an element, there'll be an interesting value for that. For instance, the heat of formation of elemental silver is 0. The heat of formation of elemental bromine is 0. The heat of formation of elemental calcium is 0. The heat of formation of all elements in their elemental state will always be 0 because remember, the definition for heat of formation is the formation of 1 mole of a compound from its elements. So remember, the delta H of formation of any element in its elemental state will be equal to 0. So that's fundamental, and you should remember that. Okay, we're going to use this chart on the next video, so we'll come back to it in just a sec. See you soon. Bye-bye.